Chapter 6, we were looking for the unique solutions for three sets of equations, and obviously each of those had three variables. So what we were actually looking at is 3D space, and would actually be what would be the 3D plane. So we're looking for the point where all three equations had the exact same value for x, y, and z, or a, b, and c, whatever it is we were trying to find. Now, what we're going to be looking at in the next exercise is what happens when there isn't a solution to all 3 points. There's not one unique solution. So to do this, I'm just going to do a quick recap of what this used to look like when we looked at linear equations. So hopefully you can remember back. We used to have, we would say there was a unique solution where we had two lines that intersect and we can find that point. We also used to have infinite solutions where the two lines were identical and it would sit on top of each other. And then we would also have the situation where the lines would parallel, and so there was absolutely no solution. So in terms of what this would look like in our matrix, so if I set this up in a matrix and did the first step where I'm just going to take two lots of row 2 away from row 1, hopefully you can see we'd have 6 take 6 is 0, 1 take 10 is -9, and 7 take 16 would be -9. And so then all we need is to get 1, 0, and we can see our y value would be 1, and then we can substitute that in to also get our x value is 1, which we could have also seen on the graph, but just to see what it would look like. If we had infinite solutions, hopefully you can see that one, because these lines are identical, one is just a scalar multiple of the other. So all three terms, the x, the y, and the constant, have all just been multiplied by 2. So if I start taking away, I end up with 0, 0, 0. And so that means they're identical, and so there's infinite solutions. If I have no solutions and I start setting up this, hopefully you can see our x's and y's are the same. So if I take one away from the other, I get 0, 0 equals -6. So obviously that makes no sense whatsoever, and so that's how we know there are no solutions. Excuse me. Now the next one is what this would look like in 3D. So we're not just looking at 3D lines, we're actually looking at 3D planes. So again, in 3D we can have a unique solution, we can have no solution, and we can have infinite solutions. But now what these will look like are our planes. So we can have 3 planes that intersect, and we can see that one point is the unique solution. Okay, so there's only one point that falls on all 3 planes. If there was no solution, we could have 3 parallel planes that never touch. We could also have 2 parallel planes and one going through both, because remember what we are trying to find is a point that exists on all 3 planes, and even though these two intersect and these two intersect, there is no point that exists on all 3. And we could also have a situation like this where we can see those two intersect, those two intersect, those two intersect, but there is no point that exists on all 3. And for infinite solutions, again, we could have identical planes, so 2 planes that sit exactly in exactly the same space, so a bit hard to show that, so hopefully you can see what we've done in that picture. And then we could also have infinite solutions when the planes are crossing and they've got a parallel line that exists on all 3. Okay, so just keep that in mind, that's what we're doing. Now the next slide, I've just taken straight from Sadler because I thought that he explained it very, very well. And as I've been saying in my previous videos, I really recommend that you read the introduction to each of the exercises because there's always excellent examples to keep us going. So yeah, here we go. We've got the same thing. So again, no solution. We can have 3 parallel planes. We could also have 2 planes that are identical and then another one. We could have that situation where we've got 2 parallel planes and one that cuts through both of them, and then we've got that intersecting pairs. And just like we did with the 2D, let's have a look at what happens when we go through the matrix. So see how, because they are all parallel, we end up with zeros and then a constant at the end, zeros and a constant at the end. So we know that's ridiculous. We can't have nothing, no x's, no y's, and no z's equaling 13. So because it makes no sense, that's how we say there's no solution. Same with this one. Now keep in mind this 0, 0, 0, 0 has come from the two planes that are identical, but it's the most important part is this one here, that the 0, 0, 0 equals 3. So that's why when we're solving, it's really important to make sure you don't just get here and go, oh, there's infinite solutions, because there could be another row that gives you no solutions, and no solutions is going to trump infinite, because obviously there is no point that it lies on all three. Same thing with this one. We've got x plus no zeros plus no x's plus no y's plus no z's equals 1. Nonsense. Again, we've just checked though that we've tried to solve for this one and we've got a 0 there. And same here. Okay, 0, 0, 0. We can't have 0 x's, 0 y's and 0 z's equal 1. Okay, infinite solutions. So when we've got three identical planes, see, we can say 0x plus 0y plus 0z equals 0. That makes sense. That's why we say there's infinite. And I'm not going to go through the rest. I'm sure you guys can read this for yourself. But again, just always checking. Don't just solve for one row. Make sure you've put at least 1 0 in your other row to make sure that it's not no solution. Okay, and we'll go through an example of these now. So we've got a set of linear equations, and now not only have we got our x, y, z equation, we've also got some p's and q's thrown in. And so we're just going to start simple, just like we did before. So we want to find the solution if p equals 1 and q equals 10. So throw those two in. Nice that we've already got a 0 in here, so we know it's not going to be too much work. So let's start by going R2 plus R1, because that's going to cancel out and give us some zeros there. Okay. Then let's go R3, take R2, because that's going to get rid of a 3 for us. And then again, remember our goal is always to have 2 zeros in one row, 1 0 in another row, and then we don't need any zeros in the last row. If we do, it's nice, but we don't have to. Then we can solve for x, z, and y. Okay, nice, just a bit of revision of what we did in 6a. Now, let's have a look at a different situation. What happens now if p equals 10 and q equals 19? So put those ones in. Again, if we go R3, take R1. So I'm just trying to work out what I've done there. Oh yeah, I broke it into two parts. Sorry guys, I know what I've done now. So I'm just doing one step at a time. So R3 take R1, and then the reason I've done that is so then we can see that we've got identical values here. So then when I take those, I can see I get my 0, 0, 0. Now remember, it's dangerous. We can't stop here. We can't go, oh, 0, 0, 0. That means there's infinite solutions. We have to keep going and make sure that these two aren't going to do something like cancel each other out as well. We need to make sure we get at least 1 0 in here to check. Okay, so don't ever stop here. We need to just do one more step. So then we do one more step. So this time I've done R2 plus R1 because that's going to give me a 0 here. Alright, so we can see that those two don't have identical x, y, and z values or some multiple of each other, so we know we're safe. So now we can conclude that there would be infinite solutions because we've got that 0, 0, 0, 0. Okay. Same one again. Now what happens when we've got p is 10 and q is 20? So again, throw those values in. This time I'm going to skip the extra step I did in the last slide and go R3, take R1, take R2. So I'm going to do, because I can see 7 and 3 is going to make 10, so I'm going to take both of these away at the same time. So I've ended up with 0, 0, 0 equals 1. Now this is when we can stop, because as soon as we end up with that gibberish that doesn't make sense, then we can just say there are no solutions, okay? Because it doesn't matter, even if this gave us all zeros, we would still conclude that there is no solutions, okay? Because we can't have 0 x's, 0 y's, and 0 z's equaling 1. All right, last example for today, guys. So we want to find the constants a and b such that the following system has infinite solutions. So we're going to have to solve our matrix with our a's and b's, still using our same rules, and try and get to a point where we can try and make sense of what a would have to be and what b would have to be to give us infinite solutions, which is of course when we have a 0x, a 0y, a 0z, and a 0 constant. So let's put that in. Think about what we've got. So hopefully again you can see we've got a 3a here and we've got 2a and 1a. So we know both of those subtracted from 3a is going to give us 0. So let's just do that as our first step. So we're going to take away r1 and r2, and that just luckily got us a 0 here as well, because when we take -1 we get 5, and 5 take 5 is 0. So be careful with your variables here. So we had to add 2b and subtract a from here. And again, don't forget about your constants. It's easy to forget about your constants when you're doing these, so make sure you did 2a and -b as well. All right, we just need one more 0 before we can start solving. So let's do row 1, take 2 lots of row 2, because then that's going to cancel out that a. Okay, make sure you agree with what I've done. So we've got -1 take 10 is 11. We've got a plus 2 lots of 2b, which is plus 4b, and then we're taking 2 lots of b, which is take 2b. Again, so now we've got our 2 zeros and our 1 0. So obviously the statement we're going to look at is this one here. So for this to give us infinite solutions, we know that 3a take b has to equal 0, and 7 take 2a take b has to equal 0. So we could write ourselves another matrix if we want to, but let's just keep it simple, and we can just go, all right, well that must mean a equals 3b's, and then we can substitute that straight into our other equation. We've got some nice easy numbers because we can see that's going to be -6b, that's going to be -b, and so we're just taking 7b, so we can see b equals 1, and put that back into our other equation, and we can see a equals 3. And if we wanted to, we could put that back to show our original equation, which is always a good idea because now we can actually see that 9 take 6 take 3 is 0, 4 take -1 take 5 is 0, and 1 take 3 take -2 is 0, 6 take 1 take 7 is 0. So we can see we would end up with all zeros there. So we can check that that would actually get us where we wanted to go. And we're also just checking that when we start solving these ones, we don't cancel out all our zeros as well. So if we went 6 take 2 lots of 3, that would give us 0, but 1 take 2 lots of 5 doesn't. So just checking we're not going to get that horrible situation where we would get 0, 0, 0, and then a constant, because obviously then it wouldn't be infinite, it would be no solution. Right, and the last part to this question is, so we've got the same equation, but is it possible now to have no solutions with this equation? So I haven't started from the beginning. I've taken it back to where we got to just that last row had 2 zeros, because this is again the information that we want. So we can still take out those 2 equations, but now we just have to think about them slightly differently. So for no solutions, we want this to equal 0, but we want this to not equal 0. Okay, this is what we know. And again, we can still go through and go, all right, we are saying that this can't equal 0, so that means b can't equal 1. So it's still the same numbers that we did in the previous examples, and so that would mean a can't equal 3, because those are the 2 that can't exist. And you're probably thinking, well, how am I supposed to work out what my values will be? But if you think about what this means, no solutions will usually mean parallel planes. So there are actually infinite no solutions, aren't there? There are lots of different ways that we can show a plane, just like if we imagine it back in 2D, when you've got parallel equations, there are infinite parallel equations. So all we have to do is pick any point that's not b equals 1, and a equals 3. So why don't we just say, well, why don't we let b equal 2 and a equals 6? And if we check by putting those in, so if b equals 2, so we've got 6, negative 12, and negative 14, so that's going to give us negative 7, all right, which is fine. We can put negative 7 in there because it's not 0. And if we put b equals 2 and a equals 6, that works. So that will give us 0, and that will give us not 0. What do we say it worked out to be? Negative 7. So there are many, many values of a and b. So in this particular question, you could have let b be anything as long as it wasn't 1. Okay? So that's enough to get you going, guys. So now that's all we need for the notes for exercise 6b. Again, I would really recommend reading the introduction to the chapter if you feel this wasn't enough for you, because the Saddle books do give you some excellent examples. I'll probably try and get the next video out to you by the end of the week. All right, thanks guys.